Alright, hello class. Today we're going to finish our discussion on 3.2, and last time we left off on Theorem 3.2.13, which is our complements. Complement of an open set is closed, complement of a closed set is open, etc. So a set O is open if and only if O complement is closed, and likewise F is closed if and only if F complement is open. Alright, so we will in this video go about proving this. Alright, so what we're going to do is start with this first statement here. We're going to start with a set O being open, then we're going to prove that it's closed. Then we're going to do the reverse, assume that its complement is closed, and then prove that the original is open. And actually what happens when we prove this first statement, this second statement essentially comes along for the ride. Okay, so really we only have to prove one of these. So let's start with our first direction here by assuming that that O is open. So let O, which is a subset of the reals, be an open set. Okay, and we want to show that O complement is closed. Okay, so to do that, what we're going to start with is, if we want to show that O complement is closed, that means we want to take a limit point of O complement and show that O complement must contain that limit point. So we want to show OC contains all of its limit points. Right, and to do that, we need to start with a limit point. So that gives us the next thing we need to do is we're going to let, of course, O be an open set, then let X be a limit point of O complement. Okay, and then from here we want to show that this X is in O complement. So we want to show X is in O complement, and that will prove that O complement is closed. Okay, well, if X is a limit point of O complement, that means for every... So I'll turn that into a comma, and then I'll say then for every epsilon greater than 0, okay, V epsilon around X, so the epsilon neighborhood around X, intersects with an element of O complement. Right? Since the limit point of O complement, then for every epsilon greater than 0, the the epsilon neighborhood around X contains an element in O complement not equal to X. Okay, now what this is actually saying, another way to say this, so in other words, okay, so if every epsilon neighborhood around X contains an element in O complement, that means every epsilon neighborhood, okay, V epsilon of X, sorry, let me say around X, contains an element not in O. Okay, in other words, V epsilon of X, so the open epsilon neighborhood around X, is not contained in O. But O is open. So that means every element in O must have an epsilon neighborhood around it that's contained completely in it. So this implies here that X is not in O, since every element of O will have an epsilon neighborhood around it that's contained completely in O. Okay, this is since O is open. All right, so if X is not in O, then X is in O complement. And that's basically it. We took a limit point of O complement, and we've proven that that limit point is in O complement. Since X was arbitrary, this implies that O complement is closed. All right, now we're going to prove the next direction, right? So here we're going to let, again, O be a subset of R such that O complement is closed. And here we want to show that O is open when this happens. Okay, so to prove that O is open, we basically want to show that for all X in O, okay, there exists some epsilon, of course greater than 0, such that the epsilon neighborhood around X is completely contained in O. Okay, so that kind of leads us in the direction we would want to go. We're going to pick an X in O and see if we can find an epsilon such that the epsilon neighborhood around that X is completely contained inside of O. All right, so there's my guidepost to help me along. So let's start with letting X be in O. Okay. Now, of course, if X is in O, this definitely implies that X is not in O complement. Now, O complement is closed. That means O complement contains all of its limit points. So, since O complement is closed, it contains all of its limit points. Which essentially tells us that, so this means X is not a limit point of O complement. All right, now let's remember what being a limit point means. Being a limit point, so remember, because we haven't really talked about much what it means to not be a limit point, but remember, if x is a limit point of some set A, then for all epsilon greater than 0, the epsilon neighborhood around x intersects A at another point other than x. Okay, if x is not a limit point, then that means this is not true. So if x is not a limit point, I'll just say LP, then there exists an epsilon, okay, where V epsilon does not intersect A at another point. Okay, in other words, where V epsilon of x contains no points. Of A. All right, and this is what we're going to use. So, since x is not a limit point of OC, this means that there exists an epsilon, of course greater than 0, where V sub epsilon around x contains no points of OC. Okay? In other words, the intersection of the epsilon neighborhood around x and OC are, that intersection is empty. Okay? So this implies that V sub epsilon, the open neighborhood around x, is completely contained in. All right, so we have that there exists an epsilon where the epsilon neighborhood around x is completely contained in O, and that's exactly what we wanted to prove. So therefore, O is open. Okay, so that proves that statement. Okay, now to do the statement with closed, right, starting with closed, well, so to prove F closed, if and only if F complement is open, basically comes down to this. It comes directly from the fact that, let's say F complement is back to being F again, right? If you take a complement twice, you get all the way back to F. So, okay, so by previous work, F complement is open if and only if F complement is closed. But F complement is equal to F, so this tells us that F complement is open if and only if F is closed. So really, you only have to prove one of them because the other one comes for free once you establish that the complement of a complement gets right back to the original set. Okay, now this brings us right along to an analog of one of the previous theorems we had for open sets we have for closed sets. Now notice it's the opposite, sort of. We have theorem 3.2.14, which says that the finite union of closed sets is closed and the arbitrary intersection of closed sets is closed. Now this is basically the opposite of what we had with open sets, because for open sets we had that the finite intersection of open sets is open and the arbitrary union of open sets is open. And how the book proves this, they do it very quickly using De Morgan's laws. So proof from the book is quick using De Morgan's laws. Specifically that, okay, if you have a finite union and you take the complement of it, it becomes a finite intersection of complements. Okay, or you could do it the other way around and get that the oops, that should be an N. Okay, and it basically comes from this. They take De Morgan's laws, which is that if you take a bunch of unions of a bunch of sets and take their complement, and the book actually uses E so that you can more generalize it. When you take the complement of all that, it turns into the unions turn into intersections, the intersections turn into so say you have an intersection of lambdas in lambda, and you complement it, then it becomes an arbitrary union of the complements. Okay, so that is the quick proof that they outline, that basically you can just apply De Morgan's laws and then use the previous theorem with open sets to complete the proof. Now this is actually a great proof. I think this is great because you've done the heavy lifting earlier and now you're just applying the things you already know. However, I do want to show these the long way, to show that you can prove these on their own. Okay, you don't actually have to use De Morgan's laws and what you already know about open sets, so you could start with closed sets. And I want to give you an example of proving something with closed sets. I think the proof we did with the open sets before was a great example of how to prove things with general open sets. Here, I want to go ahead and prove this the long way, just because I think it gives you a good look at how this works with closed sets and proving things with general closed sets. So we're going to prove this independently, all right, pretending that we don't have the result with the open sets. Okay, so just for posterity, we'll prove this directly. Okay, so we'll start with 1, which I've lost here, but we want to prove that the finite union of closed sets is closed. So we're going to let's say F1 all the way through Fn be closed sets. Then let just normal F be the union, k going from 1 to n, of these closed sets. All right, now over here I'm going to do our want to show. We want to show that capital F is closed, right? Which means that I want to show that it contains all of its limit points. So we want to show F contains all of its limit points. Okay. Then that means we want to take an X that's a limit point and show that it must be in our F. Okay, so we'll start by letting X, so let X be a limit point of standard F. All right, so if X is a limit point of F, then there exists a sequence, let's call it X sub n, in capital F that converges to X. Now if this Xn, if this sequence is in F, it's in the union of all of these. That means the sequence, I can't say it's contained completely in one of these sets. However, an infinite number of terms of Xn must live in one of these sets. So if X sub n is contained in F, then X sub n must be completely contained in at least some of these sets. All right, and so then there exists a K where F sub k contains an infinite number of terms of X sub n. Okay? In other words, i.e., there is a subsequence of Xn that's contained completely in one of these F sub k. So in other words, let me write it like this, i.e., there is a subsequence of X sub n completely contained in one of the F sub k's. Okay, so what we're doing is we're fixing this k and saying that this subsequence is contained in it. So in other words, there exists a k where a subsequence, which I'm going to call X sub k sub n, maybe not the best name for it, that's completely contained in F sub k. Now, since x sub n converges to x, every subsequence of x sub n converges to x. Okay, now that means, so therefore, x is a limit point of f sub k. Now, one thing I forgot to mention up here, there exists a sequence here. Let me put an asterisk. I'll talk about that later. This sequence is not arbitrary, right? In other words, it's not going to equal x for all n. Okay, that's the big thing there. Often that is used, often that's just implicitly implied. We don't often have to say that. Okay, so we've gotten down to where x is a limit point of f sub k, and since f sub k is closed, x is in f sub k, which implies that x is in capital F, which was the union implying f, which is the union k going from 1 to n of f sub k, is closed. Okay, so there's the proof of the first part. All right, so let's now go about proving part 2 of this. Okay, and to do so, we're going to let f sub lambda, with lambda in some arbitrary set, be an arbitrary collection of closed sets. Okay. Then let just capital F all on its own be the arbitrary intersection of the of all the f lambdas. Okay, now we want to show, once again, that f is closed. So we're going to do the exact same thing we did before by start with a limit point in f, show that it has to, start with a limit point of f, show that it has to be in f. Okay, that's always the strategy with these, is start with a limit point, of f and show it's in f. Okay, so that's what we'll do. So we're going to let capital F be this arbitrary intersection and let x be a limit point of capital F. Now this is going to be much easier to prove than part 1 was, surprisingly. That might seem a little odd, but it's because of the intersection part. So if x is a limit point of f, then there exists a sequence, okay, x sub n in capital F with x sub n not equal to x for all n in the naturals, and x sub n converges to x. Okay, well, if there exists a sequence in capital F with this, then that means this sequence is in every one of these F's because we're talking about the intersection. So then the sequence x sub n is contained in F lambda for all lambda in capital lambda. Okay. Which implies that x is a limit point of every F sub lambda. And since F sub lambda is closed for all lambda and capital lambda, I already used since, so I won't use then. So since each F lambda is closed, x is in F sub lambda for all little lambda in big lambda, implying that x is in the arbitrary intersection of the F lambdas, which is capital F, which is what we wanted. So this implies that capital F is closed. All right, and there we have it. That proves this analog for closed sets. All right, now, like I did before, I'm going to show why the arbitrary union of closed sets is not necessarily closed. So I'm going to show a counterexample. For the arbitrary union of closed sets. All right, let's consider this collection of closed intervals, right? Each one of these is a nice closed interval, and we're looking at 1 over n to 2 minus 1 over n. Okay, so if I start looking at this on a number line, when n is equal to 1, we'll get 1 and 2 minus 1. So that's just the point 1. Now that is a closed set. Then when we get to, now let me mark my 0 here and let me mark my 2. Actually, I should probably give myself a little more room. So let's say that this is 0 and let's say that this is 2. Okay. Now the next set is going to go from 1/2 to 2 minus 1/2. All right, so that would be 3/2. So right here. Okay. Then the next set is going to be 1/3. And 2 minus 1/3. Okay, so that would be 5/3. Right, then the next one will go from 1/4 to 2 minus 1/4. Okay, then 1/5, 2 minus 1/5. 1/6, 2 minus 1/6, etc. So when we union these all together, my claim is that the union for all the naturals, over all the naturals of Fn, in other words, the union as n goes from 1 to infinity of 1 over n to 2 minus 1 over n closed, is actually going to be the open set 0 to 2. Because what happens is we're getting closer and closer and closer here with closed sets, but we never actually get to 0, and we never actually get to 2. Let's see if we can prove this claim. Okay, so the first part is this infinite union, which I'll just call capital F, like I've been doing. Actually, let me just call it A. I don't want to give the impression that it's closed. Okay, but in general, so note that for all n in the naturals, okay, that 0 will be less than 1 over n, right, which will be less than or equal to 2 minus 1 over n, and then 2 minus 1 over n will always be strictly less than 2. Okay, so that's going to be true for all n. So this implies that for x in f sub n, that x will be, let me write it this way, that our x will be trapped between, right, 1 over n and 2 minus 1 over n with less than or equal to. However, it will also be trapped between 0 and 2. So this implies that x is in 0 to 2, and this will be for all n in the naturals. So for any, and I should have put that here as well, for all n in the naturals. Okay, so for any x in any of these fn's, it's also going to be contained in 0 to 2. So this tells me that f sub n is contained in 0 to 2 for all n in the naturals. All right, so that means that the union of fn's is contained in 0 to 2. Okay, if they all are, then the union of all of them must also be contained in 0 to 2. All right, so now for the next piece, I want to start. So now, let x be in 0 to 2. Right, so this gives me that x is between 0 and 2. All right, now thanks to the Archimedean property, right, there exists an n in the naturals such that x is greater than 1 over n. Now we can use the Archimedean property once again by, well, here if x is less than 2, that means 0 is less than 2 minus x, and again by the Archimedean property, I'll say there exists an m such that 1 over m is strictly is between 0 and 2 minus x, and if we move things around, again, this tells me that x is less than 2 minus 1 over m. Now, I could throw out a without loss of generality, but I do kind of want to show what's going on. So if m is greater than or equal to n, this implies that 1 over m is less than or equal to 1 over n. Okay, so this would imply, in this particular case, okay, that 1 over n, well, 1 over m would be less than or equal to 1 over n, which is less than x, which is less than 2 minus 1 over m. So this implies that x is in f sub n, or m in this case, sorry, m. Okay. All right, there's the first case. The second case, I'll just call star star here. If on the other hand, m is less than or equal to n, this implies that 1 over m is greater than or equal to 1 over n. Okay, which tells me that, well, 1 over n is less than x, which is less than 2 minus 1 over m, and that will be less than or equal to 2 minus 1 over n. And that's because since 1 over m is greater than 1 over n, here we're subtracting by something less. Okay, so in this particular case, x is in f sub n. Okay, so I didn't want to just throw it out without loss of generality. We can, but this implies there exists a, I'll call it a capital N in the naturals, such that x is in f sub capital N, which implies that that x is in the union of all the fn's, right? Because if it's in one of them, it's in the union. So it's a bit of a long walk, but we started with an x in 0 to 2 and got that it's in the union. So this implies that the open interval 0 to 2 is a subset of the union of closed sets. Okay, so we have this direction, that the countable union of these closed sets is a subset of 0 to 2, and 0 to 2 is a subset of this. Therefore, they're equal. Okay, so this is why the part 1 of that theorem is only true for a finite union, because here we found a countable union of closed sets that is equal to an open set. Okay, so that is essentially the last thing to talk about before we move on to the next section. So I will catch you all in that one. So cheers.